Okay, so we're continuing our exploration of the dynamics of systems of particles. And in this video, I want to go ahead and take a look at the concept called the reduced mass. The reduced mass shows up in orbital motion. Basically, what happens is the last time we looked at orbital motion, we have, like, say, a planet orbiting a star, or we could do, say, an electron orbiting a proton or something like that. In any event, you go ahead and you make the assumption that the big mass is glued down. Now, to varying degrees, that's a good or not so good assumption. For instance, a planet orbiting the sun, it's not too bad. The sun's a heck of a lot more massive than a planet. An electron orbiting a proton, a little less so. There's about a factor of 2,000 in the mass difference, so you're talking like 0.05%. But still probably not too bad most of the time. But we're getting to the point where we can measure things very sensitively. And so sometimes we just have to go ahead and say, well, we have to be more careful and say that the big mass isn't glued down. So I'll probably find myself referring to the big mass as the planet and the small mass as, the big mass is the star and the small mass is the planet. But really, I mean, the two masses could even be the same. It's now that we're doing this more carefully. Alright, so we'll put the center of mass right here, closer to the planet, closer to the star, like so. So we're going to take a look at this in center of mass coordinates. So in center of mass coordinates, this would be R1 prime, and that would be R2 prime. And when we assumed that the planet was glued down, the star was glued down, we were effectively moving the coordinate system to the star. So it would say that the position of the planet is, we'll call it big R. Okay, so with that, we'll go ahead and locate the center of mass. And since it's center of mass coordinates, that's locating it at the origin. So m1 r1 prime plus m2 r2 prime over m1 plus m2. Well, we can multiply both sides through by m1 plus m2, and we get that m1 r1 prime plus m2 r2 prime equals 0. And we'll also note that this gives us that r2 prime is equal to minus, is equal to minus m1 over m2 r1 prime. Alright, so let's express our capital R just in terms of our r1 prime. So R is equal to, well, r1 prime minus r2 prime. So that will be r1 prime. Then r2 prime is minus m1 over m2 r1 prime, so this becomes minus a minus. So that gives us 1 plus m1 over m2 r1 prime. And then we'll rewrite this as r1 prime is our r, which is the thing that we can actually measure, versus our r1 prime, which is the actual orbital distance, over 1 plus m1 over m2. Okay. So with all of that out of the way, we can now write for our central force. So for a central force, the acceleration of the planet, m1 R1 double dot. Oh, we can make that look better. Prime. Because that's the distance that matters. Excuse me. Will equal the force as a function of the separation, and then to get the direction right, since this is an arbitrary central force, we're allowing for the possibility of repulsion. So it would be positive if it's repulsive, negative if it's attractive. So the direction vector will be r over r, like so. Okay. So we came up with our expression for r1 prime, so let's just go put it in so we can get this expressed in terms of our observables. So if this is r1 prime, I differentiate this twice, I get double dot here, and I'll get double dot there. So m1 r double dot, that's our observable, over 1 plus m1 over m2 equals my f of r times r over r, which is just giving me a unit vector in the capital R direction. Alright, and then to clean this up a bit, I can multiply numerator and denominator by m2. It'll make it look prettier anyway. m1 m2 over m1 plus m2 r double dot equals f of r over r. Alright, so with that we will now go ahead and define the reduced mass mu to be that. So we're defining the reduced mass to be that. Alright, so with that definition we can then write mu r double dot equals f of r over r. Now we should ask ourselves, what does this mean? So we had been pretending that the big mass was glued down, and now that we're letting that go, we can still say that from the perspective of an observer on the big mass, we were almost right to pretend that the big mass was glued down. From that observer's perspective, all we have to do is replace the little mass, m2, by this reduced mass. And it's called the reduced mass because if you look at this, you'll see that it's always going to be less than whatever the little mass is. So here m2 is the little mass. It's going to be less by a factor of m1 over m1 plus m2. Now in the case of Sun and Earth, this m1 over m1 plus m2 is darn near 1. In the case of, say, electron around hydrogen atom, it's something like, 1999 over 2000, or I think it's actually more like 2000 over 2001, something like that. Yeah, 2000 over 2001-ish. So it's still a number really close to 1, but not quite 1. In the sense atomic physicists can measure things at the parts per billion level. That matters. Alright, so let's go ahead and apply this to gravity just to see what we get. So with gravity now, we write as mu r double dot equals minus g m1 m2 over big R squared times the r unit vector. Alright, so we'll go ahead and put in what the unit mass is. We'll have m1, m1, m2 r double dot over m1 plus m2 equals minus g m1 m2 over r squared times the r unit vector. Okay, and so we can go ahead and cancel out our big mass M2. Sorry, I misspoke just a moment ago, but the same idea applies. Big mass is M2, so we cancel it out. And then to get it to look like what we've had before, we'll have M1R double dot, so this is what a person would write, equals minus G M1 times M1 plus M2 over R squared, R over R. Okay. Now, so what we've done is we've replaced the mass of the star with the mass of the star and the planet. Alright, so you recall before when we played with this, we got t squared equals 4 pi squared over gm2 a cubed. That was Kepler's third law. So nothing changes except now this m2 becomes m1 plus m2. So now we write as t squared equals 4 pi squared over g m1 plus m2 a cubed. So when we say that we study orbital motion to weigh, you know, a planet or a star or whatever by looking at something orbiting it, the analogy I like to use is saying it's like weighing a dog with his fleas, and then you assume that the mass of the dog isn't that different without the fleas. Now, there are exceptions where, you know, astronomers can detect that the mass of the planets compared to the mass of the star is noticeable. So a good application here is looking at exoplanets. So if that's my center of mass right there, there's my planet, we'll call that big M. Oh, sorry, my star, we'll call it big M. Here's my planet, little m. But it's going to be a big planet. So let's say, there we go, like so. We'll have this be, like, say, on the order of the mass of Saturn or Jupiter or something like that. Although now the technique is getting to the point where we can detect Earth-like things if everything is just right. It's just harder to do. So anyway, the deal here will be these two always have to stay in a line. So the planet orbits the center of mass with its period, which means the star orbits the center of mass with its period as well. And you can almost deduce the radial speed of the star. You can't see the planet. But you can almost deduce the radial speed of the star looking at the red and blue shifts that this causes to the star spectrum. Obviously, you've got to be very, very precise to see it, but it can be done. So from this, so we can say, well, VCM is 0. That's be equal to V of my star plus little m, V of my planet, over m plus m. So we can sort of deduce the velocity of the star. I'm hedging here because you don't know the plane that you don't know what the tilt of the orbital plane is relative to your line of sight, and so you usually just use this to get yourself a bound on the mass of the planet. But you can do some other tricks too. Anyway, velocity of the planet be minus m over m times the velocity of the star. This doesn't sound awesome, but believe it or not, this is good enough for us to deduce the semi-major axis of the planet's orbit. And we can deduce the mass of the planet, believe it or not, because you actually do know the mass of the star. Certainly, without going too far afield, in an astronomy course, you would find out that the spectral class of a planet, so its unique spectrum, turns out to be very much tied into the size of the star. You can look it up in a thing called the Hertzsprung-Russell diagram. And it also turns out that the luminosity, the brightness of the star, also ties into the mass of the star. So you can measure the mass of the star a couple different ways. Like I say, you do it spectroscopically, the Hertzsprung-Russell diagram. Photometrically, you can deduce the intensity, put that all together, and you can work out the mass of the star that you're looking at. So once you know that, you can then work backward to get a bound on the mass of the exoplanet that you're looking at. Now, in the early days of looking at exoplanets, it's certainly got a lot better. We can now, under certain circumstances, find roughly Earth-sized planets, a little bigger yet, but it's basically right there. In the early days, the planets that they were finding were what were called hot Jupiters, which were planets that were at least the size of Jupiter, if not bigger, orbiting their star at a distance that was shorter than that of Mercury. Now, if you think about it, this means that it's yanking its star around the hardest, which meant that it was easiest to detect. So this is sort of an example of selection bias, just something that, when you do observational work, you need to be aware of. Your technique may more easily pick out some things rather than others. As the technique got better, you're able to find smaller planets at bigger orbits, and now the technique is getting pretty darn good. Okay, we'll pick up in the next video. The next few videos are going to be taking a look at collisions.